You multiply the I components together. Well, that's negative 10 I dot I. Outer plus 35 I dot j plus 6 j dot I minus 21 j dot j. This is the long way of doing it. I dot I, how much of any vector is in the direction of itself? All of it. Yeah, all of it. And what's the size of a unit vector? 1. So this is just 1 times the cosine of 0. In other words, 1. So we get negative 10. I dot j, how much of I is parallel to j?
0.
0. So 0, 0, then minus 21, and we end up with negative 31.
Wow.
So ultimately, you just multiply that like components. Multiply the i's together, multiply the j's together. You're done. So what is force equal to? I'm not, yeah, that is right. I'm not quite sure everybody was ready for that yet. Questions on that before we get back to the derivation we're doing? We can actually make this is the calculus version. So AB dot dx. All right, so what is force equal to?
Mass times acceleration.
So this is the mass of A times the acceleration of A dot dxa. And what's acceleration equal to? Besides force over mass.
I'm about to say. Well,
The definition of acceleration.
change of velocity, change of time.
Or calculus version.
Yeah.
dv dt
Yeah, dv.
times dot dx. So I can just take that dt and just shift it over. And so make this mass of A dv dot dx dt. And what's dx dt?
That is velocity.
So this becomes mass of A dv dot v. And so ultimately here, I have f dot dx is equal to mav dot dv. We can throw a cosine into it. I'm going to just make the assumption v and dv are in the same direction just for the simplicity, simplifying it some. So if I integrate both sides, over here I have ma v dv from some initial velocity to a final velocity. But I guess actually initial speed to final speed. And what's the integral of v dv?
1/2 v squared.
So we have the mass of A times 1/2 v squared from v initial to v final, which is mass of A, 1/2 out front, times vf squared minus vi squared, which is 1/2 mass of A vf squared minus 1/2 mass of A I squared. And that's equal to the integral of f dot dx from some, I guess, some initial position to some final position. We take it one step further. For those who have had physics before, you probably know it. For those who haven't had it, you're in for a very special treat.
Good. Oh.
Questions to hear before we do the special treat?
I think. Punch it, Chewy.
All right. This 1/2 MAVF squared, that's too much for physicists to write, so they came up with something to call that. They use a big letter K and call that 1/2 MV squared.
Yeah.
So this now becomes this integral of force dot dx from some initial position to some final position is equal to K final minus K initial, or the delta K. They, of course, have words for these things. This, on the left-hand side, this integral of the force dot dx, this is work. Matter of fact, since this force here is the total force, this is the total work. So I'm going to write work total is equal to the change in K, and K is what's called kinetic energy.
Yeah. Oh boy.
And that's the special treat. We have a word for it. Now, one of the reasons why I go through that, one, in physics, I want you to see this all stuff comes from somewhere. It's not like I could present it as in, here's a formula, all right, new situation, new formula, but there is a flow to it all. There's been only one physics formula in this entire course. The rest of it's just math and definitions. F equals ma is the only physics formula so far.
Because Newton said so.
And there's evidence to support that, I believe, right here. This expression right here is known as the work energy theorem. Now, I don't know why they call it a theorem. It seems more like a work energy definition, but that's about the right way. It's known as the work energy theorem. Now, almost every single formula that we deal with in this course, as you get into more and more complex physics, you'll find, wait a second, that was just a special case. F equals ma is an example. That is turns out to be a special case. But there is one formula that actually holds true. You're working on your Nobel Prize winning dissertation. The formula for kinetic energy is still the same. So, the one formula that I do expect you to have memorized, that on a moment's notice I can ask you, what's the formula for kinetic energy? And you should know it. 30 years from now, when I run across you and I go, wait a second, I remember I had you at Forsyth Tech in physics, what's the formula for kinetic energy? You should know it.
What will happen if he cannot
He will kill you.
memory? he will.
He stabbed
You need to know it.
He will stab me.
All right, so
this like men.
when I asked, and I will do a quick story first. When I was doing IT consulting, we were at the training camp up in Illinois, and at some point we're all there doing coding, and these people come in and say, everybody up the desk, we're going to do jumping jacks. And I, for one, and I wasn't the only one, looked at him strangely, and then they said, we are serious, get up now, we're going to do jumping jacks. Because they didn't want us sitting the entire time without any exercise. So, I am serious. When I say, what is the formula for kinetic energy? I want, in response, in unison, it's going to be a chorus of angels here, 1/2 mv squared. Don't use the words, just do the letters. 1/2 mv squared. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
Almost a chorus of angels, but we'll get there. That was nice.
Is that just going to happen randomly through like a test? Just you'll call it out?
Not during a test.
Okay.
Whoever answers
No,
first
it
gets
would
an A.
disrupt our train of thought.
So, we have this 1/2 mv squared. At this point, I do need to talk about some types of forces. We have the F-tong, but we can also categorize forces a slightly different way as conservative forces. And non-conservative forces. Not liberal, non-conservative. Now, some of you have had this before, and so we'll just sort of open it up for that. Why do you suppose they're called conservative forces?
They conserve energy.
Yes. Now, for those who have been spending too much time with the life sciences, conservation does not mean using less. Conservation means that the total stays the same. There is an official definition of conservative forces. If you take F dot dx, a conservative force here, and you take it on a round trip, you get 0.
Is there supposed to be the line, or not the line, the circle? And
Yes. Circle means that we're doing, it's a line integral because it's dx, which is a one-dimensional thing. And the circle means we end up back where we started.
Ah, okay.
So it's like an integral from A to A.
Yes. Dx, if it were dA here, and this was an area integral, if we did that, that means we're doing a surface, doing the entire surface of a closed object. Now, the easier way, instead of going through and going, all right, let's do this integral here, see if I get 0, the easier way is a checklist. I'm going to list down all the forces that we have dealt with that are conservative so far.
Oh boy. Gravity.
Done.
Oh. Oh.
There is one more that we will deal with in this class. Gravitational force, this includes the specific, the special case of weight and also the generalized force. And then there's the ideal elastic force, which we haven't done yet, but that's another one that. In 252, the electric force and magnetic force are also conservative.
Oh, electric force.
Non-conservative forces, everything else.
Normal.
So physicists, as they are going through this stuff, all right, they recognize there's this thing called energy. Now, in my mind, energy is just a math thing. They came up with this thing so that it will work. Non-conservative forces do not conserve energy. So if I do non-conservative work, which would be the integral of the non-conservative forces, dot dx, well, it's not 0. It should, well, that would be equal to the change in energy. So we have the total work is equal to the change in kinetic energy. The non-conservative work is equal to the change in total energy. Since all forces are either conservative or each force is conservative or it's non-conservative, if I'm looking at the total work, that should be equal to the non-conservative work plus the conservative work, because those are the choices. That should be equal to the change in kinetic energy, because that's the total work. Non-conservative work, I just sort of laid out, is equal to the change in energy here. Plus work conservative is equal to the change in kinetic. And it depends on how you want to go about this. Let's bring K over. So we have delta E, the change in the total energy minus the change in kinetic is equal to the negative conservative work. So this introduces the idea that there must be another kind of work. Another kind of energy.
Oh boy.
Well, if you think about this, this is classical physics. All objects in classical physics have 3 things. You can add more to it, but 3 that I care about right now. They have mass, they have a position, and they have a speed. Energy associated with speed is kinetic energy. Energy associated with mass is known as rest energy. All of you know the formula, although perhaps you don't realize it at the moment.
Mm-hmm.
And position
Is potential.
potential energy. And for that, I use a capital U. which I assume comes from the German, but not 100% sure. It's the letter that's used in graduate school. I don't use PE. All right, let's deal with rest energy. This is mainly a trivia aspect. The formula for rest energy is
Equals MC squared.
the one thing that we change from that is that it's m sub 0 c squared. M sub 0 is the rest mass. Okay. And the difference is if I'm trying to find the mass of an object, as long as the object is at rest relative to me as the observer, I can find its rest mass. If I'm trying to find the rest mass of an object that's traveling near the speed of light, I am not going to get its rest mass. That will be sort of a relativistic mass.
So with that energy, what, like, well,
Where does it show up?
what unit is that in? Like, what unit is energy in? Like, when you're measuring it, like, how many units is it? Because, you know, C is a big number.
Oh, you want not the unit of measure, but sort of scale? Is that what you're going for?
Well, yeah, oh, that's what I mean, the unit of measure.
Unit, oh, all right.
Because C is a big number.
Well, if you go back to the work-energy relationships here, energy should have the same units as work. Work is a force times the displacement.
Yeah, so that's like,
And so
Newton meters.
that would be Newton meters, which is too much for physicists to write. And so they came up with the one-word thing, the joule. So a joule is, by definition, a Newton meter in the context of energy and work. Later on, we will deal with Newton meters that are not joules. So just please be careful about that.
It's watts, right?
oh yeah, well,
No, there is, when you get into torque,
Yeah.
Newton meters is just Newton meters. It is not joules.
it's yeah, how many newtons per how many meters?
So 1 joule, by definition, is one, that's a 1 there, 1 Newton meter. And the 3 lines mean by definition.
Oh.
In math class, that was not the symbol that I got from the math people. I got the equal sign with the triangle over it. Okay. But I've done that in previous semesters, and I usually get blank looks, so I'm not quite sure what they do nowadays.
I'm saying that's a lot of energy because C is a big number, usually probably meters per second.
It is. So if I took a match, it has a certain mass to it, certain rest mass. I can strike it if I collect all the ash that comes off of it, and then I find the mass of all the ash and then the burnt match. There should be a small difference. That difference is the energy that got lost, that got transferred from its rest energy into, well, ultimately, kinetic energy. Now, some textbooks will start going into other types of energy. In chemistry, you also talk about chemical bonds in terms of energy. The chemical bonds is a potential energy. Thermal energy is kinetic. Everything is going to fall into one of these 3 categories here. So, back to here. Since energy is kinetic plus potential, rest energy does not fall into classical physics. That falls into what's known as semi-classical physics, which it only would matter near the end of 252. So we assume that we are not having any conversion from mass into radiation for the sake of this course. So this energy here is kinetic plus potential. Also, if we're just dealing with these 2 right here, this is also known as mechanical energy. So this is delta K plus delta U minus delta K is equal to negative work conservative. The kinetics cancel out. And what you're left with is conservative work is equal to the negative change in potential energy. These are the work energy relationships. There are a number of problems where this is my starting point. Questions to hear? So now, if I ask you, what is the formula for potential energy? The proper response is which one. There is not a formula for potential energy. Some people get brainwashed into thinking MGH. That is just one specific case. It turns out every conservative force has a potential energy formula.
Oh, good.
Yes. So if it is weight, so the conservative force is weight, the potential energy formula is, or we can just go mg, is mgh. We'll derive that, sort of setting it up right now. If you're dealing with g mass 1 mass 2 over r squared, the potential energy formula is negative big G mass 1 mass 2 over r. If you're dealing with the elastic force, which is negative k delta x, this is the lowercase k, this is the spring constant, we'll deal with that later, then the potential energy is 1/2 k delta x squared. And those are the three that I have listed up there. MGH shows up a lot, so that's why some people begin to think that's the formula. That is just a formula. Please do not use MGH when it's not appropriate.
Can I use MGH for gravitational
I'm guessing that's, yeah, the MGH is based on position.
So MGH, this is used if G is relatively constant. Little g, relatively constant. So when you're dealing with planetary systems, you tend not to use that. Or if you're dealing with someone's going from the moon to Earth, or when we deal with escape speed, we will not be using a GH, we'll be using this.
Yeah.
So let's derive that MGH. I have an object going from some initial height to some final height, so it's going to fall, the object's going to fall. I know that work conservative, the conservative work is equal to the negative change in potential energy. First, let's establish force diagram. I have an object that's falling. What are all the forces acting on it?
Gravity acting down on the object.
That's
You
it.
can do better than just gravity. Thank you. Weight or force due to gravity.
Yeah.
It's the only force acting on it. Is it conservative? No.
Yes. That's the only. Yes.
It's not the only one.
It is indeed a conservative force. And so therefore we can use this equation right here. I know that the conservative work is equal to the negative change in potential energy. Let's see how Orange is doing today. Because that's not working particularly well either.
And the red from before was good.
This is F dot dx. The force and displacement are in the same direction, so we can now make this just F dx. The force is mg. And dx, my initial position is hi, my final position is hf. And so this becomes mg h final minus h initial. Oh. I think I do this every semester. I'm off of minus sign here. So. No. When you integrate, you have to. You go from the smallest to the largest value. So this is hf to hi. And that's equal to the negative u final minus u initial. These markers. Don't forget it right now. Let's try this one.
I'm sorry.
They're trying, okay. They're giving it their best.
You put them back in the same place you got them from, Professor.
I know. Which is ui minus uf. So what we have here, if I distribute, is mghi minus mghf equals ui minus uf. What is a value? What is a formula for u which would make this work?
Well, we have MGH. I did MGH in this case.
All right, mgh would work. Give me another formula for u that would also work.
GM1 over R squared.
No, I'm looking at this formula. I'm looking at this right here. I want some formula for u that will make this work. mgh is a formula that works. What is another formula that works? By the way, there's an infinite number of formulas that work.
Cool.
Oh, good.
I'm just asking for one more.
I don't know. Mr. Fox, what is another?
Mr. Fox, my brother
Honestly, just get out.
Is that a FC over MG?
I won't
U over MGH?
It's FC over mg.
No,
No,
it's
it's not
saying-
division. That's a table where that's just a underlining.
Well, we can have,
All right, so let's look at it slightly differently.
UI.
6 minus 2 is equal to 4. What else would be equal to 4? What other subtraction problem would be equal to 4?
Minus 4.
There seems to be some relationship here.
They are
What's that?
minus 0.
Directly proportional.
I don't know how to.
Not directly.
It's not directly. Oh, it's.
I don't know how to.
Mina, say it again. Recognize plus some constant. Because the constant is going to cancel out. Since the constant, there's an infinite number of constants, so that's why there's an infinite number of solutions. It's mgh plus some constant. This gives us the freedom of being able to determine where is the potential energy equal to 0. We don't have to make 0 the ground. We don't have to make it the center of the earth. We don't have to make it where the object is. We can make 0 anywhere we want, because the formula really for any of those potential energy formulas is what I've written there plus some constant. So we really don't, without knowing where it's 0, we can't really tell you the value of potential energy anywhere, but it doesn't matter because what matters is the change in potential, not the actual potential number itself. And on that note, Verizon says you have done your time.
Yes, sir, President.
You're waiting for it.